Hey everybody, welcome back to physics. I hope everyone's doing well. Today we're going to talk about an entirely different topic, something that we haven't discussed all year. All year we've been discussing the concept of mechanics, how things move, why things move. But now we're going to be discussing a concept that's been very mysterious for most of human history. We're going to be discussing electricity, later on magnetism, and eventually circuits. Now, if you really think about electricity, it does seem kind of like a magical phenomenon, right? Let's say electricity was off for all of human history and then I just turned it on today. The fact that you get shocked when you touch your doorknob, lightning strikes in the sky, that would seem like magic to us, right? Throughout all of human history, we know these little kind of shocks happen. We knew that this kind of electrical phenomena would happen, back in the 16, 17, 1800s, there used to be people that would put on electrical magic shows, and it would be these amazing things that you would see, and they would call these electrical magicians electricians, and we still use that word today to discuss people who work in the electrical field. So we want to talk about what electricity is at the most fundamental level. We want to strip everything away and really understand what's going on here. And this question of what electricity is gets at the heart of some really important questions in science. Things like, what is the nature of stuff? What is stuff at the most fundamental level? How does it interact with each other? And how does the electrical phenomena manifest itself on a larger scale? This discussion will hopefully give you a better appreciation of electricity in general. Think about it. You're watching me on your computer screen right now. I have lights, I have a TV. This is because we mastered this fundamental force of electricity and magnetism, and us better understanding it, we could use it to our advantage. All right, so what is electricity? If you ask that question and really think about it, it's hard to really pin down what's going on here. We know that things happen. We plug in our technology in the wall. We know something happens when we flip the switch. But we want to strip away and start at the very basic of what's going on with electricity. So we're going to start our discussion with this idea of electrostatics. If we break down this word, this quite literally means stationary electricity. The study of electric charges at rest. Now, this actually kind of gets us started with our discussion. What is an electrical charge? Just like how mass is the intrinsic property for the gravitational force, this idea of electric charge is the intrinsic property of the electrostatic force. All right, I guess we'll dive in and get started. We have this high-tech setup, my little remote control. Go to the next slide. It's not working. There we go. Nice. All right. So before we discuss electricity, we need to talk about what stuff is at the most fundamental level. You guys learned in chemistry that if we zoom in really close to matter, all ordinary matter is made up of these particles, which we call atoms. Now, what's interesting is this word atom comes from the Greek word which means indivisible. Now, as you guys know from chemistry, we can actually divide up atoms into composite particles. You know that atoms are made up of what we call protons, neutrons, and electrons. So reviewing chemistry, we have this densely packed nucleus for every atomic particle. Densely packed nucleus with protons and neutrons hanging out here. And then we have electrons that can move freely outside of the nucleus in what we call the electron cloud. From chemistry, you learn that protons are positively charged and electrons are negatively charged. And that idea of charge, positive and negative charge, is at the heart of what electricity truly is. Protons are positively charged, neutrons are neutral, and electrons are negatively charged. Something I want to talk about briefly. You've probably seen this picture of atoms all over the place. If you Google what an atom picture is, that's how I found this. It'll look something like this. But this is a bit misleading. Atoms aren't you can't perfectly see where the nucleus is, you can't perfectly see where the electrons are, but it does help us better understand the basics of what's going on here. And later on in the year, we'll talk about how this picture is a bit fuzzier than you might think it is. Okay, so just to review, Protons, positively charged, electrons, negatively charged, neutrons are no charge. But the fact that all matter is made up of atoms, and protons are positive, electrons are negative, that means all matter is electric by nature. The interaction between these charges is at the heart of what's going on with the electrical force. Next slide. Okay, so that's what we're talking about when it comes to electricity. We get to talk about what's going on at the atomic and the subatomic level. But when we really see electrical phenomena on our scale, when you get shocked by your doorknob, when balloons stick to the wall, that's macroscopic objects getting charged. So an object is said to be charged if there's an imbalance of positive and negative charges. So if you count up all the charges and you see that the positive charges equal out with the negative charges, that object is neutral. But if there's an imbalance of charges, then we say that object is charged. The more of an imbalance we have, the more charge we have on that object. If you, scrape your feet across the rug, you might be charged, but you might have a small imbalance. That's why you don't really get shocked. But the more you do it, then eventually you can actually get shocked because you're increasing the imbalance of charge on your body. Now, we know there's an imbalance of charge, but how does that charge actually get imbalanced? To charge an object, it turns out that only electrons can be transferred from one object to another. Why is that? Well, it's because the electron is about 2,000 times less massive than the proton. From what we understand about inertia, it's much easier to accelerate and move around an electron with much less mass than it would be to move around a proton. If the electron was a penny, the proton would be about the size of a bowling ball. Not only that, but protons and neutrons are fixed inside of the nucleus. So to move protons around, you actually have to do nuclear physics, which is really hard to do. It takes a lot of energy to move around a proton, but it doesn't take as much energy to move around these electrons. So to charge an object, when an object requires a charge, it's because electrons are being transferred to the object or electrons are being transferred away from the object. All right, I feel like I'm going fast. I'm gonna try to slow down a little bit. Okay. So, just like we said, neutral objects have an equal number of positive and negative charges. Positive objects then, if an object is positively charged, that means it's missing electrons. Only electrons can be transferred. So if we take electrons away from the object, now there's an imbalance. There's more positive charges than negative charges. It didn't gain protons, it lost electrons. And when you have a negative object, that means that object has an excess of electrons. We dumped more electrons on that object than it had originally. More negative charges than positive charges. That object is now negatively charged. All right. Next. Okay. Now here's the interesting thing about the electric interaction. You might know this, but I really want to dive in and discuss why this is interesting. When it comes to like charges, if you have two positively charged objects or two negatively charged objects, those objects are going to repel one another. Like charges repel, while opposite charges attract. Now, this is the big difference between the electrostatic force and the gravitational force. The gravitational force is only an attractive force. Any object with mass, any two objects with mass are going to gravitationally attract one another. When it comes to electrostatic force, you have to look and see what type of charges we have. If you have like charges, they're going to repel one another, where opposite charges are going to attract one another. It's very important. Okay. Flying through here. All right, so what about neutral objects? So like I said, like charges attract one another. Like charges repel one another, unlike charges attract. But what if I have a charged object next to some kind of neutral object? So, and I'm talking about macroscopic objects here, large objects where there's a large number of positive and negative charges inside of the object. Neutral objects actually attract both positive and negative objects. How could that possibly be? Well, it's because in neutral objects, charge become polarized in the presence of a charged object. So imagine this for a second. We have a positively charged rod and then some kind of neutral sphere. We bring that positive object in. Without looking at the charges, we know that there's an attractive force here. But how can we explain why there's an attractive force? It's because as we bring in this positive object, it causes the electrons inside of the object to move closer to that positive object. And a very important thing when it comes to electrostatics and electricity is to remember that electrons are the things that are moving around. And if you could understand that fundamental idea, then you could understand the story behind all of these interactions here. So electrons are moving around. All of the electrons in the sphere are going to try to get closer to this positive object, leaving behind positive charges on the other end of the sphere. The electrons move one way, the positive charge left behind. The charge in this sphere became what we call polarized. We like to sound smart in science, but that word polarized just means separate. The charge is separated inside of the sphere. Is this sphere still neutral though? Well, if you add up all the positive and negative objects, it's still a neutral object. There's still a balance of positive and negative charges, but the charges separated. So this neutral object is now polarized, and you'll feel an attractive force here. Well, what if I brought in a negatively charged object instead of a positively charged object? Again, electrons are the things that can move. And if you understand that like charged repel, unlike charged attract, if I bring in a negative object, the electrons in the sphere do not want to be near that negative object. So the electrons would run away from that negatively charged object. The electrons will all gather on the other end of the sphere, leaving behind positive charges. So that neutral object would get polarized in the other way, and it would still feel an attractive force. So this all means that attraction is not a test of whether or not an object is charged, because neutral objects will be attracted to both positively charged objects and negatively charged objects. All right, I want to show you a little simulation here. Now, if you have a balloon in your house, what I want you to do right now, take that balloon, rub it on your hair, rub it on your beard. And you'll notice that that balloon will stick to the wall. Why does that happen? Well, we're going to explain why this happens through this idea of polarization. So here's our balloon. Now, obviously, this is what we would see in the real world. We see a balloon, we see a sweater, we see a wall. If we take this balloon and we rub it on the sweater or rub it on your hair, you'll see that balloon would stick to the wall. If we can actually see what's going on with these charges, it helps us explain what's actually going on in this case. So we're going to reset. Now I want to see what's actually going on with these charges. Everything here is neutral. If I add up all the positive and negative charges, the sweater is neutral, the balloon is neutral, and the wall is neutral. Now I take my balloon and we rub it on the sweater. Notice what happens. By rubbing the balloon on the sweater, the balloon steals those negative charges on the sweater. The sweater is left with a net positive charge, and the balloon now has a net negative charge. When it comes to simulations and like scientific diagrams, you always want to ask yourself, okay, what is this trying to teach me, and how could this simulation not quite be correct? Now, did I take every single negative charge away from that sweater? No. But I did take a lot of the negative charges away, giving a net positive charge, but there still would be some negative charges here on the sweater. So I took all of those electrons, because electrons are what can move around, positive charges left behind. Now, why does the balloon stick to the neutral wall? Watch closely. As I bring this negative balloon to the wall, watch what happens to the charges in the wall. Whoa. So as I bring the balloon nearby, those electrons in the wall move away from the balloon, leaving behind these positive charges. A negatively charged balloon sticks to the neutral wall because the electrons want to run away, leaving behind this tiny little pocket of positive charges. I did not charge the wall. The wall is still neutral if we add up all the positive and negative charges, but the electrons just move away from the balloon, charges separate and become polarized. So, like charges repel, unlike charges attract, and if I have a charged object near a neutral object, whether it's positive or negative, it's going to be attracted because of this idea of polarization. All right. I want to go back. Here we go. I wish I could ask you guys questions and interact with you a little bit more, but at least this is something. All right, I have a puzzle for you based on what we've talked about so far. Consider 4 objects. We have object A, object B, object C, and object D. Here's what we know about these objects. We know C and D repel one another. We know that A attracts both B and D, and we also know that A is repelled from a negative object. I want you to tell me the charge on each one of these objects. Is it positive? Is it negative? Is it neutral? There could be more than one answer for each of these objects. Could be. So I want you to work out this puzzle. Send me your answers and I'll tell you if you're right or wrong. But by figuring out this puzzle, it helps us really make sure we understand what's going on with the electrostatic force between these objects and identifying the charge in each object. So I don't know, pause the video, do it now, and I'm going to keep going. Okay. The next thing I want to discuss is a device that we call an electroscope. I really tried to go out and get the materials to build an electroscope. I realize it's probably not a good idea, so I don't have an electroscope to show you, but I can at least show you gifs of what an electroscope is. When we get back in class, hopefully I'll be able to show you the electroscopes we have in our classroom. So an electroscope is a device that we use to detect the presence of charge. It does not detect whether a charge is positive or negative if the electroscope is neutral. It only detects if there's charge nearby. So notice what's happening here. This device here is the electroscope, and then we have a device, we have some kind of object that's moving near the electroscope. We know that object is charged because as it moves near the electroscope, the leaves of the electroscope separate. That would happen whether this is positive or whether this is negative. So, based on our current understanding of electrostatics, let's see if we could explain why, whether this is positive or negatively charged, the leaves will diverge in either case. Okay, first, imagine we're bringing in a positively charged object to the electroscope. What does it mean for an object to be positively charged? It means that it's missing electrons, because remember, electrons are the only thing that can move between objects. Electricity, when you have a circuit, is really the flow of electrons. Electrons was moving from one place to another. So again, positively charged object, we're missing electrons. We bring it close to the electroscope. What happens to the charges inside of the electroscope? The electroscope is neutral. So when we bring in this positively charged object, where do the electrons in the electroscope want to go? Well, the electrons in the electroscope want to run upwards to this positively charged object. So the electroscope remains neutral, but all of the electrons run up towards this positively charged object. And if the electrons come up, what's left behind is net positive charge down here in the leaves. Now, if both leaves are positively charged, do they want to be near one another? No. So the electrons run up, the leaves are positively charged, and they repel one another. What we did was we polarized the electroscope, and it detects that there's charge nearby. So one more time, Neutral electroscope, electrons run upwards, leaving behind positive charges, making those leaves want to separate from one another. So, what if we bring in a negatively charged object? If we bring in a negatively charged object, think of what the electrons want to do and how they'd like to move. Well, the electrons don't want to be near that negatively charged object. So the electrons in the electroscope run away from the negatively charged object, leaving behind positive charges up here. The electrons run down the electroscope, making these leaves negatively charged. And when the leaves are negatively charged, they're going to want to repel one another. All right. Makes sense? Hope so. Okay. That's how an electroscope detects the presence of charge. It polarizes the electroscope in either way, depending on whether this object is positively charged or negatively charged, making those leaves separate from one another. Okay. Next thing I want to discuss is how charges could move inside of materials. Take a look around your room for a second, find a wire that you could take a look at and hold on to. If you notice, all wires are made of what looks like rubber, right? But if we chop the rubber and look on the inside, there's metal inside of those wires. Now, we want wires to carry electricity. That's their only goal, right? So we have metal inside because charges can easily flow through conductors, but we put the rubber on the outside of the wire to protect us for when we touch that wire. So when charges can move freely through the wire, charges move freely in what we call conductors, and they don't move freely, they're blocked in what we call insulators. Two different types of materials. Okay. What happened? No. Go back. There we go. All right. So conductors and insulators, types of materials. How do charges move in these types of materials? So the first type of material is a conductor. And this is a type of material where charge can flow freely. Maybe you remember from chemistry, but all metals are great electrical conductors. The reason for that is, if you remember, their valence shells are about half filled, so it's very easy for electrons to jump between all the different atoms inside of a metal. It's basically a sea of free electrons. Very easy for them to jump around to different atoms. All right, conductors allow charge to flow freely. Now, what happens when we place charge on a conductor where charge can move freely? We want to imagine how those charges actually move. So, let's say I have a conductor and I take some kind of charges and I throw them on one end of the conductor. Charges can move freely through the conductor. So what happens is they distribute evenly over the surface of the conductor, leaving the inside of the conductor with no charges. This is the way that charges distribute themselves, so they're furthest away from one another. Because if these negative charges don't want to be near one another, so they distribute evenly over the surface, leaving the inside with no charges. The amazing thing here is when you watch workers work on like high voltage, high current power lines, you might ask yourself, well, how do they protect themselves so they don't get shocked? You might want to say, well, maybe they wear some kind of insulator to block the charges. But it turns out they actually wear what we call a Faraday suit. They wear an entire suit made of metal. And that seems crazy, right? Why would you want to wear a suit of metal to work on these power lines? It's because if they do get shocked, those charges would go across the surface of those metal suits, leaving the meaty insides safe. I'm going to link a video for you guys to watch. This is a great YouTube channel. It's called Minute Physics, and it discusses what kind of suit you'd want to wear if you were struck by lightning. Okay. So those are conductors. It keeps freezing on me. There we go. All right, so those are conductors. Next are insulators. Insulators are a type of material where charge cannot flow freely. Examples of insulators are like the rubber on the edge of your wires. Wood is a great insulator, and believe it or not, pure water is a great insulator. Now, common knowledge says that water conducts electricity really, really well, but that's because there are ions dissolved inside of the water, allowing charge to flow freely through the liquid. But if we took out all the ions in the water and just had pure water, believe it or not, it's actually a great insulator. So, if I were to throw charge on the edge of an insulator, yes, I could charge up the insulator and throw all these charges here, but it's much harder for the charges to move around. So they actually kind of get caught in this section of the insulator. They can't really move around freely, where if I throw charge on one end of a conductor, they'll distribute themselves evenly over the surface. Charge tends to stay put when you put it on an insulator, where it flows around the surface of a conductor. All right. Let's see. I'm freezing again. There we go. Okay. Let's see how long we've gone. 26 minutes. Okay. All right. So the next thing I would like to discuss is how we could actually measure charge on an object, right? We know that there are objects that can have more charge and objects that can have less charge depending on this imbalance. So we want a way to quantify and measure how much charge could actually be present on an object. Now, from what we talked about, we know that electrons are what's moving around from one object to another. So can't we just count the imbalance of charges on an object? Like if we have 3 extra electrons, we know that object is negatively charged and it's negatively charged by 3 electrons. Or if an object is missing 5 electrons, we know it's positively charged and it's positively charged by plus 5 of these charges, right? From chemistry, we know that the charge on a proton and electron are equal in magnitude but opposite in sign. So this magnitude, this amount of charge on each one of these particles is what we call the elementary charge. And the elementary charge is the smallest isolated charge observable in nature. It's the charge on a single proton or electron. In nature, you won't find charges any less than the elementary charge. We can't chop this elementary charge in half. We can, but you won't find that in nature. So for now, in general, the smallest amount of charge that you could find is an elementary charge. You won't find half of an elementary charge anywhere. Okay, that's the charge on a single proton or a single electron. But this is a really tiny amount of charge. When we charge up objects macroscopically, it's very hard for us to actually count the amount of protons or electrons. So this isn't the SI unit of charge, the metric unit of charge. It's just one way for us to track how much charge is in an object. But this is really important. It's important to remember that charge comes in discrete packets. If an object becomes charged, it's because an electron moved over, gaining a lump sum of charge, or an electron moved away, losing a lump sum of charge. But the SI unit for charge is what we call a coulomb, denoted by capital C. Named after a French dude, I believe. Charles d'Auguste de Coulomb. And a coulomb is a huge amount of charge. 1 coulomb is equal to, what is this? 1,000, million, billion, trillion, quadrillion, quintillion, sextillion. 6.25 sextillion electrons, or either gaining or losing, in order for you to have 1 coulomb of charge. So 1 coulomb of charge is 6.25 times 10 to the 18 elementary charges. That's how many you need to have a coulomb of charge. And you could use that to flip it around. The charge on a single elementary charge is 1.6 times 10 to the minus 19 coulombs. These are important numbers to remember. I want you to think of coulombs as like a bucket, right? If that bucket is fully filled with electrons or protons, then you have 1 coulomb of charge, and the amount of charges you have in that bucket is 6.25 times 10 to the 18 elementary charges. You can half fill that bucket, and if it's half filled, you have half a coulomb, and you have half those number of charges inside of the bucket. If I only place 1 charge inside of the coulomb bucket, then you have that bucket being filled by 1.6 times 10 to the minus 19 amount. That's how many coulombs you have. Okay. Now, this is a very small amount of charge in coulombs on a single elementary charge. A guy by the name of Robert Millikan in, I believe it was the early 1900s, back when we didn't really have much technology to do it, he accurately measured how much charge is on a single electron back in that time. We'll talk about the experiment he did a little bit in the future, but it's amazing that in the early 1900s, he figured out almost exactly how much charge on a single electron, times 10 to the minus 19. Accurately measuring a small order of magnitude like that. All right, frozen again. This is nice, this is just like class. The board freezing on us. Okay. So this means that any charged object has to have some integer multiple of elementary charges. Remember, we can't have half an elementary charge in an object. So if you have 1 extra elementary charge, 2 extra elementary charges, that's how you actually gain or lose charge, because we have an imbalance of these charges. So the total charge on any object can be found by finding how many elementary charges it either has or how many elementary charges it's missing, right? How many electrons it has or how many electrons it's missing. The total charge Q, which is what we use to denote charge in our equations, lowercase q, don't ask me why. The total charge of an object Q in coulombs is equal to the integer multiple of elementary charges. Is it 1 elementary charge, 2 elementary charges, 1,000,000 elementary charges, 1,000,000,000 elementary charges? But it's going to be some multiple of the elementary charge. Remember, this letter n cannot be half. It has to be an integer multiple. All right. And with that, I think I'm going to finish up this video for now. We did talk about a lot. Usually this would take longer in class because we'll have some kind of discussions, some kind of questions. I feel like I kind of flew through this. So I'll let you sit on these ideas for now. I'm going to post some questions where you're trying to find the actual charge on an object. And we'll continue with this stuff in the future. Thanks for sticking with me. Remember, it's an integer multiple of elementary charge. You can't have half of an elementary charge on an object. All right. Hope everyone's doing well, and we'll see you soon in the next video. Stop me.